it's really hard to compete against cake, but I'm going to do my best. So my name is Avraham Chapman. You guys can all call me Avi. I'm a research student at the University of Adelaide, and I'm very glad to be able to present to you my first ever paper. That is a really long name. I only get 12 minutes to talk, so I'm not going to actually say it. But the content of the paper is a technique called ASIF, so I'll refer to that. Now, let me introduce ASIF. ASIF stands for Adversarial Suppression of Identity Features. Now, it's a technique that's broadly applicable in any area that uses supervised learning. So I intend to take you through the background behind it and a bit about the theory. I'm also going to, as an aside, show you a technique for adversarial training, which is very, very useful and should be universally applicable. I intend to show you the results that we reduce the amount of data needed for training, and also that this technique will be resilient against the presence of dirty labels, which is an inevitability in any real-world situation. And finally, we'll be talking a bit about some interesting effects on the feature vector that's produced by ASIF. So, first of all, the background. Now, ASIF is not actually a domain adaptation technique, but we do derive some of our inspiration from domain adaptation, so I thought I'd tell you a bit about it. So, domain adaptation is a technique for training a model on one domain and then applying the model in another domain. For our purposes, a domain consists of a feature space and a marginal probability distribution. Now, feature space is the set of things that you can measure about something. The marginal probability distribution is something about the shape of the measurement. Now, to put that in a more intuitive sense, if you think about all the countries in the world, for any given country, you can measure various things such as the area, population demographics, or even the probability of multiple birth given a pregnancy. Now, that last point comes in the shape of a curve, and that curve is going to look different from one country and another, or one domain and another. Now, adversarial domain adaptation is a subset within domain adaptation, which basically involves a minimax game, where we attempt to simultaneously increase our accuracy on classification while decreasing our ability to determine which domain the data came from in the first place. So we all know that deep learning models are really, really good at fitting to the data. In fact, if the model is big enough, it can fit to completely arbitrarily assigned labels. So what we've done is we've taken the process and divided it into two subproblems. Now, there's nothing unique here, that everyone does this. We have a section which takes the sample input and produces a feature vector, and another section which uses that feature vector to perform classification. Now, where we do things differently is we conceptualize the features in the vector into two different types. One is class-wise discriminative features, and the other one is identity-wise. Now, class-wise features, they're ones that can be used to tell the difference between one class and another. So let's say cats versus dogs. Look at the whiskers. Now, as an aside, I've actually been using the whiskers as an example for 6 months now. And the other day, someone came up to me and said, Avi, did you know that dogs have whiskers? And no. So anyway, I've never seen a dog with whiskers, but I've never seen a cat that doesn't have whiskers. So, in my reckoning, whiskers are a really good feature to use to determine one class from another. Now, on the other hand, we have identity-wise discriminative features. These are ones within a class that you can use to tell one individual from another. Again, returning to the whiskers, you might look at the number of whiskers or the length of the whiskers. So we have one type of feature that's useful for classification, and another type of feature which is a distraction. Now, we hypothesize that if you have a classifier which is trained to use features that are from individuals, then it's going to overfit that data a lot faster and overfits the individuals within that training data set. So we want to use adversarial training in order to get rid of those features. So to do that, for each sample, we assign two things. We assign a label, and we assign an identity. So the label will be like cat versus dog. The identity, well, in reality, is just a number, but it's a unique number within that class. So we then train to predict the class label while failing to predict the identity. And since each one is unique within its class, it has the effect of pushing together the feature vectors within the class and pulling them apart outside the class. So to do this, we're going to use a gradient reversal layer. Now, this was first proposed as part of the DANN model, seen here, I'm sorry. So the DANN model has 3 modules. It's got, in green, a feature extractor whose job it is to take the sample and create a vector of features that describe that sample. And then in blue, we've got a class predictor. It takes the feature vector and predicts the class. And in pink, we have a domain predictor. Now, in the original concept, the idea was that the domain predictor would predict which data set it came from. It can be used in other ways too. So in the example I have here, the cartoon versus photo. Anyway, so between the domain predictor and the feature extractor, we have the gradient reversal layer. Now, since this reverses the gradient during the training, it has the effect that the class label gets more and more accurate. The class prediction, I should say, gets more and more accurate, whereas the domain prediction gets worse and worse. And in the meanwhile, the feature extractor itself, it learns to produce feature vectors that have a lot of class data and have no domain data. Now, we've taken this idea and we've improved upon it. The original gradient reversal layer, the way it worked was the data would pass through in forward propagation, and then on back propagation, it would multiply the gradient by -1 times a tunable hyperparameter, lambda. Now, this value for lambda was set on a schedule. This schedule was worked out beforehand, and it had to be set exactly right. If it was too aggressive or too lax, then the training would fail. So we found a way to get rid of it. We replaced it with dynamic gradient reversal. Now, this works on the insight that the opposite of right is not wrong. The opposite of right is confusion, and we can measure confusion. So we look at the logics coming out of the domain classifier and look at the entropy level. We want to aim for a maximum level of entropy. So to do this, we borrow a page from control theory. We have essentially a proportional only PID controller. We calculate the loss that we would see if we had maximum entropy. And then as we train, we monitor the loss and calculate the difference between that and the ideal loss. And that allows us to tweak the lambda hyperparameter as we go. So this means that the domain classifier, it gets better and better and better during training until it starts to get too good. And then it gets pulled back, and then it gets better. And in that way, it stays near the sweet spot. Now, I'll tell you a bit about our model. That should look familiar because it's basically the DANN model. The major change we made here is that the domain classifier is now an instance identifier. And in this way, we hope to optimize that. Now, there's a lot of math there. I'm not going to go through it, but basically it just minimizes the error in one area, maximizes the error in another area. Now, since the identities are unique within each class, we actually have to have a separate identifier module for every class. Now, we work with a small number of classes in the experimentation, but we're going to need to be able to scale it up. So to do that, we had to share the first 2 layers of our MLP. The weights are all shared, which allows us to scale it up much higher. So let me tell you a bit about the results. We hypothesized that we would be removing any kind of identifying data from the feature vectors while increasing the amount of class identifying data. So what we did was we wanted to first check if we actually successfully removed the instance data. To do that, we grabbed a small classifier, like a 1-layer classifier, and we trained it on the feature vectors output from the feature extractor. One trained with ASIF and the other trained with a standard cross-entropy loss. And what you can see here is that in the case of the standard one, we were able to achieve a very low loss from the classifier, meaning that the classifier had a lot of data to work with in making its classification. However, when we used the one with ASIF, the classifier was clueless. So this tells us that we were successfully removing these identity data. On the other side, we wanted to look at classification performance. Now, the whole idea here is that we're trying to eliminate overfitting. So it stands to reason we should be able to train a model on less data and get as accurate performance on the evaluation set. And what we have here is we have ASIF versus 3 other techniques with various subsets of the CFAR10 data set. We have MNIST in the paper as well, but you guys are welcome to go look that up later. And as you can see, ASIF did better than the other three techniques. In fact, at 40,000 records, ASIF had better accuracy than 50,000 for the others. So this tells us we succeeded in reducing the overfitting. Now, we didn't actually set out to try to tackle noisy labels when we did this, but it was a useful side effect and we wanted to explore it. So in order to do that, we introduced two types of noise into the data set. One is instance invariant noise. Now this is a very simple kind of noise. You roll the dice, and if your number comes up, then you flip the labels. That's not very realistic. So we also tried instance dependent noise. And the way this works is if a sample is difficult or in some way ambiguous, it is more likely to have its label flipped. This reflects reality. How we actually did that, I'll leave as an exercise to the reader. Just read the paper. And we chose two other techniques to compete against. Now these two techniques explicitly went out to try and solve the issue of noisy labels. And here's our results. We got 6 levels of noise, and we found that ASIF beat cross-entropy and generalized cross-entropy in every case. But in the case of P. Huber, it was competitive. It beat it sometimes, and sometimes P. Huber won. But what's really interesting is that in the case of high noise, 80 or 90%, ASIF bested everybody. Okay, so the final thing I wanted to tell you about is the effect of on the feature vector of using ASIF. Now, I talked to you earlier about how the whiskers on a cat can be used to tell the difference between a dog and a cat. And it can also be used to tell the difference between individual cats. Now, this kind of thing, the fact that the feature could be used in both roles, can lead to a disentangling effect. You might have one number which describes whether the whiskers are there at all, and another number which describes how long the whiskers are. One becomes an instance feature, the other becomes a class feature. So looking into this, we wanted to explore it. And what we did there was we trained another classifier on the feature vectors. This time the classifier was trying to figure out the class. So we trained it, we recorded the accuracy we obtained, and then we checked the weights of the classifier to identify which of the features in the vector was the least useful. We removed those features from the vectors, and then we grabbed a new classifier and trained it again. We repeated this process, going from 512 down to 0. So the results of this is that for the first 400 or so features, it made no difference whatsoever to the accuracy. Now this could mean that they're useless in terms of classification, or it could mean that there's a lot of redundant data in there. But once you get down to about 60 left, the standard trained classifier begins to lose accuracy. That tells us that you need at least that many features in order to encode the class data. But with ASIF, we get down to 20 before we start to lose accuracy. And in fact, it doesn't seriously lose accuracy until you only have 10 features left in the vector. So that kind of feature compression is very interesting, and we hope to explore this in the future. So to reiterate, the ASIF's achievements are that we have a greater, we require less data for training, and we came up with an interesting dynamic gradient reversal layer, which is universally applicable. In fact, I should probably tell you, we tried putting that back into the original DANN model and reran it, and we got the same performance. We just didn't need the schedule, so that's very interesting. So in conclusion, it's been a pleasure to tell you all about this, and I'd be happy to take your questions.
Yeah, looking at your problem formulation, it looks very similar to contrastive learning. Are there any advantages or disadvantages in your method versus standard contrastive learning?
Yeah, you're not the first person to notice this. They are very similar, especially in the effect, but there are differences as well. When it comes to the clustering effect, with contrastive learning, you tend to get clustering across the entire feature vector. If you were to do it in a TSE, you'd get a lot of nice little blobs. When you view the result of ASIF, you see absolutely no clustering. And the reason for that is because all those useless features in that final one I showed you, there is no redundancy in that data. That data has absolutely no class data in it. It's all other things. So we get this compression effect. And if you were to scale down to just the subspace that includes the data, then you're going to see that same kind of clumping.
Thank you.
So perhaps just one last question before we go to the next one. So you showed some results on CIFA-10. Did you do other experiments on other data sets?
Yes, we did an experiment on MNIST. There were several other data sets, but those are the only two that made it into the paper.
Yeah, thanks. I think in the interest of time, we just move on to the next one. Yeah, thanks.
Thank you very much.
So the next one, feature similarities and correlation.